Good morning, everyone. Up to now, we have talked about phase diagrams and phase transformations. And I already told you that the phase diagrams and phase transformations are the most important topics in the material science class. And you should understand this, okay? And if I give you some phase diagrams and also some cooling rate, and ask you guys to interpret this is the phase diagrams and also the phase transformation, and you should be able to use your own words and to tell me what happens, what kind of microstructures and we will get at this cooling rate. Um, Today we are going to talk about applications and processing of metal alloys. Before we move on to this topic, and I want to tell you that last time and when we talked about the harness, and I told you we have four different harness measurements. And one is called Rockwell harness, and one is called Brinell harness. The third one is called Nooper. The fourth one is called Vickers. And so these are four uh, different harness measuring approaches, and they are for different skills. For example, Vickers and this is Noop harness. They are for micro the harness. For if you are taking this is the ME lab, or you are going to take ME lab in this semester, and you will know um, how to use the hardness tester and to measure the hardness using the Rockwell equipment. And we use HRC, and H means the hardness, R is Rockwell, C here means the skill. We have skill A, skill B, and skill C for Rockwell hardness. And so I will give these questions, and this is the curiosity for you guys to um, take the ME lab. So you will learn a lot of information, techniques about harness testing. And now we are going to continue our talk about this material science, and then we are going to talk about applications and processing of metal alloys. And here are today's objective. We want to learn ferrous alloys. And before we get started, I want to ask you a question. Can somebody tell me what is the ferrous alloys? If you do not know and you can just think about it, I'll give you 30 seconds to think about ferrous alloys, what is a ferrous alloys, and what condition an alloy and should be called the ferrous alloy. Um, okay, some students, thank you very much. Some students raise their hands, and I think you know. Um, just wait for several minutes, and I want to hear other people's response. Okay, guys, and I found several students are already give me the correct answer, and yes, and ferrous alloys means that and this alloy contains the iron element. Iron Fe is the iron element. If alloys if an alloy does not contain the Fe, the iron, and we will say, so this is the non-ferrous alloys. Non-ferrous alloys, they have totally distinct these mechanical properties when compared with ferrous alloys. So here is a classification of metal alloys. So this you can see the metal alloys. This is the root, and for the first level, and we distinguish these metal alloys into two categories. One is ferrous, one is non-ferrous. And why we focus on ferrous? Because the ferrous materials they have been commonly used in modern engineering applications. So that's the reason we focus on the ferrous. For the ferrous, that means this guy contains alloy, it contains iron. And then we differentiate this material further, and we will have a steel, and we will have a cast iron. So both of them, they are ferrous alloys. And what's the difference between steel and cast iron? So this is the steels, and we can have low alloy. So this is a low alloy and high alloy. This is a low alloy, and we have this is low carbon, medium carbon, and high carbon the composition. And so for here, low carbon, we have plain, and we plain means that, and we have iron and carbon, and but it's only two elements. And then we might have high strength low alloy if we add some alloying elements in addition to the iron and the carbon. And for medium carbon, we also have plain and the heat treatable one. Okay, so for high carbon, we have plain and we have tool. This is the tool steel. Tool steel um, is very hard, as the name suggests. They um, serve as a tool, so that it needs to be very hard. So another branch is high alloy. This high alloy, we have the tool, we have the stainless steel. The stainless steel. We are very familiar with stainless steel because we use stainless steel to build to make our utensils that we eat meals with. And so this is one branch, the steel branch, and another branch is cast iron. Now cast iron has several have several different the subcategories. One is a gray iron, and second one is a ductile or called nodular iron, and the third one is white iron. The fourth one is malleable iron, and the last one is compacted graphite iron. So you need to be very careful about this. And these five different cast irons, and they have totally different mechanical properties. And we will talk about this one later. And first, we talk about classification of uh, metal alloys. Metal alloys for ferrous here. And so, how can we classify these metal alloys? We need to use a phase diagram, right? So this is a phase diagram. So here is our phase diagram. So here is the iron zero composition. So this is 647 uh, percent of iron, and so we can see here, and still, if the carbon composition is less than 1.4, uh, 1.4 with percent, it is here. Okay, we call it steel. And otherwise, if the carbon is higher than 3, more than 3 here, so this is called cast iron, from 3 to 0.5 with percent, and we call this as the cast iron. So the cast iron, the microstructure for this cast iron, and we know that it has ferrite and graphite and also cementite. Cementite is Fe3C. So here we have this kind of microstructure. And for the low alloy, we have um, low carbon, medium carbon, and high carbon. As you can see, it's based upon the carbon composition. If the carbon composition is less than 0.25 weight percent, we call low carbon. Low carbon, this is the name plain, the high strength, this is the low carbon alloy. We made some alloying elements here. Additions, we don't have addition for this plane, but for this was uh, high strength. This is the low material, low carbon iron. We have chromium, vanadium, nickel, and molybdenum. So for example, here is example. And so here is an example. Hardenability. Hardenability for this one, it is very hard, right? This hardenability, we use the plus sign to indicate hardenability. Hardenability is ability to be hardened, as the name suggests. And also the tensile strength along with this is a elongation. and this automated strength. We call this automated strength. They can be very low. Um, this is the it is can be very low. For here, it uses as these auto cars and structured steel or this low carbon low carbon alloy, low carbon steel. For high strength low carbon alloy, and we can use the bridges, towers, press vessels. For medium carbon, which has the carbon composition from 0.25% to 0.6 with percent, and we have plain also heat treatable with this is the chromium, nickel, and this molybdenum. So for example, 1045 is commonly used one, and 4340 is also commonly used one. And this comparison in terms of hardenability and ultimate strength, along with this is elongation ability for elongation. And so this is applications here. Um, Also for high carbon, and we have so this is the wear application for here. This is the drills and source dies. So for this high carbon, they have very high hardness. So they also plane and tool. We have this is alloying elements: chromium, vanadium, molybdenum, and tungsten. And for this stainless steel, and we need to have the chromium. This chromium, the percentage of chromium needs to be greater than 11%. One thing I want to mention, some textbooks say 11%, some textbooks say 13%. And each way will be okay. For this class, if you write 11% for the chromium, and we will have this is a stainless steel, and I will be fine. For this stainless steel, high temperature application, turbines, furnace are very corrosion resistant because it is called stainless steel, right? Stainless means that it is difficult for this kind of material to be corroded. And increasing strength and the cost and decreasing ductility. And so you should know that. And the strength and the ductility, they are two competing mechanical properties. And as I said, for one material, uh, you cannot want this guy to have very high strength, but very high ductility. It is impossible, because strength and ductility they are defined in opposite directions. Questions regarding this slide? No question. We talk about these low carbon steels a little bit deeper. And so here, composition of 5 plain low carbon steels and 3 high strength low carbon steels. On this 1010, I want you guys to know the last 2 digits indicates the carbon composition. It is 0.10% of carbon. This is 0.20% of carbon. So this A36 is austenite and 36, ASTM 36. It is commonly used for this shipbuilding industry for A36. A56 16 on grade 70. So you can see they have different carbon this carbon composition, and also this manganese composition of manganese. And there's other um, alloying elements. For this one, we have on the 0.20 the percent of copper. And for this one, we have 0.25 the silicon. For high strength low alloy steels, for example, this A means austenite, and we have A4040, and we have different uh, materials, and we have different this carbon composition along with the manganese composition, and also we have other these compositions here. You can see, and they have different mechanical properties. And then we look at this as mechanical characteristics of hot-rolled materials and typical applications for various plain low carbon and high strength low alloy steel, low alloy steels. So this is tensile strengths are given, yield strengths are given, ductility are given also. And here are the typical applications. Um, by the way, I want to say this 1010, so these automobile panels, and also this is the nails and this wear, and they are being used for these applications. For high strength low alloy steel, so this austenite, whenever you see this A, and it means austenite, we have different tensile strengths, yield strengths, along with ductility, and also these are typical engineering applications. So low carbon steels, and there are several observations, and they contain less than 0.25% of this carbon, uh, are responsible to heat treatment, but can be strengthened by cold work. So this is low carbon steel. Um, we will not say it is not hard treatable. Um, Microstructure contains ferrite and pearlite constituents, and soft and weak with outstanding ductility and toughness. Machinable, weldable, and less expensive. On the contrary, for high strength, low alloy steels, and we have uh, contain other alloying elements such as copper, vanadium, nickel, and molybdenum in combined concentration as high as 10%, and possess higher strength than the plain low carbon steels, and most of them may be strengthened by heat treatment. In addition, and they are ductile, formable, and also machinable, and they are more resistant to corrosion than the plain carbon steels because of the alloying elements we added here. Any questions regarding this slide? No question. Move on to the next one, and we talk about the medium, the carbon steels. So this is medium carbon steels. So here is the designation, ASI, SAE designation, this UNS designation, and here are the composition, the ranges about nickel, chromium, molybdenum, and other alloying elements. Um, and I hope you guys can take a look at this table very, very carefully, and especially for your uh, senior design or other projects, and you want to build something, you need to select the materials. So medium carbon steels. So for here is uh, AISI numbers, tensile the tensile strength and yield strength, and we have this is ductility, and this typical application are given here also. For medium carbon steels, we have uh, this is range of carbon, and they can be heat treated by austenitizing, quenching, and then tempering. And plain medium carbon steels have low hardenability. Addition of chromium, nickel, and molybdenum improved hardenabilities. Then we talk about high carbon steels. So for this category, they usually contain 0.6 to 1.4 weight percent of carbon, and it's hardest, very hard, strongest but least ductile, used in hardened and tempered condition. Because of their excellent hardness, they have good wear resistance and capable of holding a sharp edge. As a result, they have been used as tools, as dies, cleaning blades. The tool and the die steels are high carbon alloys, usually containing chromium, vanadium, tungsten, and molybdenum. So here is a high carbon steel, and commonly used high carbon steel ASI number, UNS number, and this composition. And here are the typical engineering applications. And then we talk about the stainless steel. The predominant alloying element is chromium. As I said, at least 11% of chromium is required and can be enhanced by nickel and molybdenum additions. So three classes: martensitic, ferritic, ferritic, or austenitic. So these are three different kinds of stainless steel: austenite, austenitic, ferritic, or this austenitic, martensitic, ferrite, or the austenitic, stainless steel, martensitic, ferritic, or austenitic. So here is the table of different stainless steels. We have so this is so we have ferritic, austenitic, martensitic, and so here is a precipitation hardened wall. The different the stainless steels. And then we talk about how we get this steel, the refinement of steel from ore. So here is the schematic representation of the furnace. So we have iron ore, put the iron ore here. And so here is a slag, here's a molten iron, and so here is the layers of coke and iron core. And here is a refractory vessel, this is a vessel, refractory. Why we use the refractory? Because they have very, very high melting temperature. So this is a gas. We have, this is the limestone, this is a coke here, the blast furnace. And heat generation, and the carbon plus oxygen, and we have this carbon dioxide, and reduction of iron core to metal. And so this is carbon dioxide plus carbon. We have this carbon monoxide, which is poisonous. Be very, very careful. And then this guy uh, have reaction with this is the Fe2O3, and we can have 2Fe, and then plus this uh, three carbon dioxide molecules. And purification. So this guy will be is a gas that will be released. And so you have this is CaO plus CO2. We have CaCO3, and so we have CO3 silicon and plus this one. We have this the slag. And ferrous alloy-based alloy, steel cast iron. Uh, Nomenclature for steels: ASI and this SAE. So here's a plain for this one: plain carbon steel, re um, sulfurized for machinability. So this is contains um, manganese, molybdenum, nickel, and molybdenum. So where this one is, okay, it is with percent of this is carbon multiplied by C, multiplied by 100. For example, 1060 means that this gas carbon composition is 0.60%. On stainless steel, you should know that the chromium composition must be equal or must be greater than 11%. And to be safe, we will use 30% of chromium.